What up? We're back. All right. So where did we leave off? Right. We were talking about the acid catalyzed mechanism for D2O. All right. So this is one of these extra slides that I should include, I think, just in case it gets that deep. Um, so really the main question that I would be asked that would prompt me to pull up this slide would be like, why do we quench at that specific pH? And it's because the acid and base catalyzed mechanism is kind of evenly happening. Like there's a 50-50% chance there. So this is when the rates of both of them are at their lowest. I believe that's kind of the rationale. Um, right. So they cross the minimum typically around at their slowest net rates overall. That's why they push the system right to the bottom of V. So I still don't know exactly why. Why is the minimum here? Is it because both acid and base reactions are about happening or are happening evenly, so they are in competition with one another? I think that's why. So what is the acid catalyzed mechanism for D2O? There are two possible pathways, with the main one being the emetic pathway. Um, so I guess I can add an image of the pathways there too, which is shown here. Um, Save image with Google Lens. What is that? Whoa, that's new. That's kind of cool. All right. Save image as, let's do desktop somewhere. Um, so I'll put a title here. Acid catalyzed mechanism for the yeah, and then this will be so what this is. Next question. The minimum isn't because the acid and base are compete or cancel each other. It's because each pathway is weak there. So when you add them together, the sum is the smallest. At that pH, the acid and base contributes are roughly equal. but they're both small. Let's unpack that. Ignore the water term for the moment. Yeah. Acid term gets smaller as pH increases. Base term gets bigger as pH increases. Use term alone is monotonic. When you add them, you get a U/V shape curve. Dropped a lot. The acid term is small. It's not very big, so both contribute or small at the same time. If sum is the smallest, that is your pH min. Mathematically, the minimum is roughly where we're equal. That's often what people mean when they say curves cross. But important, equal is not competing. They're adding to get the smallest possible total. So there are independent parallel pathways. Okay. You get a minimum at a pH where both are individually as small as they'll ever be at the same time, given their difference P. Okay. That's actually pretty interesting. So, um, acid versus or P or rate pH dependence or rate dependence, rate of acid slash base catalysis of exchange as it depends on pH. So technically, okay, so the question is, why at pH 2.5 do we quench the reaction? So at this pH is when the rates of acid and base are at their lowest. They are happening roughly in equal proportion here, but that is not to say they are in competition with one another. They are parallel paths. This is just the pH where it is too basic, where it is basic enough for the acid path to be slow and acidic enough for the basic to be slow as well. So this implies that the base catalyzed mechanism is more efficient? I'll ask my professor about this, honestly. If acid and base pathways have the same intrinsic strength, the crossing might be near the middle, but base catalyst is intrinsically more efficient than acid catalyst. So why is the base... So that's like another question. Why is the base... Why is the base catalyzed mechanism more efficient? I think it probably has something to do with the pKa. No. I don't know, honestly. So this is one path. So I need to add the other one. Oops. And so here's scheme 2. Scheme 1. Scheme 2. Think about the pH. Okay. The pH dependent rate is this. Per mole of OD, the reaction is way faster than per mole of that. You actually see this from pH checks. At the minimum, the acid base terms were equal. Asymmetry, better acid than base. Oh, I see. Okay. Yeah, so I was a little bit right. The pKa. So, okay. That makes complete sense, honestly. So why is the base catalyzed mechanism more efficient? Because a peptide bond acts more as an acid than a base. So it's 15 to 17. This is more specific. Peptide is much better at donating a proton to a base than accepting a proton in the carbonyl. Carbonyl is usually buried. This is another good reason why. The carbonyl is usually buried in the H bond network of the peptide backbone. It's already fairly satisfied as an H bond acceptor, rather further protonation is energetically costly. Cool. All right. So the acid catalyzed mechanism is this up here. So what slide were we on? Here. All right, I need to go to the bathroom. right. Okay, so what else could they ask me? So what do I usually explain here? So this is like the overview of HDX MS. Um, so I would say here, initially what you would do is start with like a protein of interest in a state you would start with a protein in a state that you're interested in investigating, right? So in this case, it would be cytochrome C with heme bound. And you would dissolve this in D2O, where at the moment what you do, an exchange reaction would begin to occur. So over here is the base catalyzed mechanism for what happens when you dissolve your protein in D2O. So along the peptide backbones, there would be this OD. So what would this be called? Um, I don't want to say alkoxide because I don't think that's the right term for it. Deuterium oxide. Yeah, deuterium oxide. So deuterium oxide right here would abstract a proton from the peptide bond, and there'd be some resonance stabilization of this, and then the nitrogen would act as a base, um, abstracting a deuterium from D2O, regenerating the deuterium oxide and creating your deuterated peptide bond. So here you would quench the reaction at around pH 2.5, which would stop the exchange process from occurring, or at the very least slow it down as much as possible. And then you would carry out digestion with, say, pepsin. Okay. So we probably should ask the question, what is pepsin? Pepsin digestion. It's an enzyme that begins digestion of proteins in the stomach. It is produced in the stomach lining. Okay. So this is an enzyme. Pepsin is an enzyme that operates in acidic conditions to cleave a protein in certain positions to create peptides. So it does this with hydrolysis. So it's like the hydrolysis mechanism. There's trypsin as well. This be schematic mechanism of pepsin hydrolysis by serine protease. Okay. Pepsin is synthesized and secreted by chief cells in stomach lining. There's an active form known as pepsinogen. The zymogen form prevents the enzyme from digesting the cells that produce it. The activation of pepsinogen into pepsin is a key step in the digestive process, where pH is typically due to secretion of hydrochloric acid by partial period cells that undergoes a conformational change. This acidic pH cleaves a specific peptide bond where pepsinogen molecule, resulting in the release of the active enzyme. That's pretty cool, actually. It shows a preference for cleaving peptide bonds adjacent to aromatic acids, such as phenylalanine, tryptophan, and tyrosine. That's something probably to do. It shows a preference for cleaving peptide bonds adjacent to aromatic residues. It's attributed to aspartic protease nature. I wonder if we could find the PDB for this. Looks like I've already looked it up. Human pepsin in complex with pepstatin. So where is this active site? This is like aspartate residues, which I'm not seeing anywhere. What's this? I don't know. That's probably as far as I need to go for pepsin, I think. So maybe I could look up why does pepsin operate in acidic conditions? Because its structure and catalytic mechanism are dependent on the presence of hydronium. Hydronium is, yeah. The low pH in the stomach, central pepsogen in the porcine pepsogen. So this is the inactive form. Looks very unstructured. There's not a lot of secondary structure there. acid-base catalytic mechanism. Two aspartic acid residues in the active site. Acts as a general base, abstracting so aspartic acid has a pKa of around I think it's 2. Yeah. Oh, never mind, it's 4. It's not even on there. Where's that image I liked right here? Yeah, it's around 4. So honestly, you could just say aspartic acid and glutamic acid are both 4. So if it's in an acidic environment, those are mostly going to be I guess deprotonated. So then why does it yeah, pH 7 it's deprotonated. But here it's fully protonated. So why does it act like a base? I mean, I know these things can act both as acids or bases depending on its environment.
This explains why pepsin only works in low pH environments due to the low 5 of zinc can break peptide bonds. In this reaction, one of the aspartic acid residues has a hydrogen bound to it, and the other one holds a water molecule in the active site. The water molecule loses a hydrogen to one of the aspartic acids, and then the rest of it binds to the carbonyl carbon, forming an unstable tetrahedral adduct in the peptide. Through one more set of electron shuffles, the peptide bond between carbon and nitrogen is finally broken, and the two sides of the cleaved peptide leave the
Hmm. So where is this 215? Right here. Yeah, 32. And so this is the active site right there. Interesting. So I mean, I guess this is more exposed to the solvent. So what was the question we had? This will carry on, and we wait to quench reaction with acid, effectively locking deuterium substitutions in the protein. The protein is then digested with, say, pepsin to create the deuterium-labeled peptides. They might ask, are there any other um, proteases? This is what I think it's called, protease. Yeah. So yeah, there are. So this is like one of these areas of study, because pepsin, because ultimately we want higher resolution, and depending on the protease you use, it'll cut in certain positions. So there's other ones. Endopeptidase is what makes this protease reaction. So it cleaves preferentially the hardest areas. Pearly. So let's add that. Are there other Yes, this is an active subject of study given this is an active subject study given whichever protease you use determines the resolution of the experiment, really. The issue here is that the protease must operate at these acidic conditions. So pepsin is the one most often used given this is the enzyme our stomach uses to break down proteins. I think that's fine. Then it's fed through a standard LC-MS setup. So we probably need to 13. What is LC MS. Liquid chromatography mass spectrometry is a powerful analytical technique that combines two methods to separate, identify, and quantify substances in a liquid sample. First, liquid chromatography separates the sample's components into individual parts. Then a mass spectrometer measures the mass to charge ratio of these separated components to determine their molecular weight, structure, and quantity. Okay. All right. LC-MS stands for liquid chromatography mass spectrum. I can't spell. Liquid chromatography mass spectrometry. All right, so physical separation capabilities with mass. Liquid chromatography separates mixtures with multiple components. Mass spectrometry provides spectral information that may help identify or confirm the suspected identity of the separated component. MS is not only sensitive but provides selective detection, relieving the need for complete chromatographic separation. LC-MS is appropriate for metabolomics because of good coverage and wide range of chemicals. All right. It's a method of physical separation in which the components of a liquid mixture are distributed into two immiscible phases so they don't dissolve each other, i.e. stationary and mobile. The practice of LC can be divided into 5 categories. Immiscible, right? Yeah. Absorption. Among these, the most widely used variant, reverse phase. Maybe this talks about it. There we go. A major analytical challenge is the analysis of deuterium incorporation without unacceptable loss of deuterium label during sample handling. With nearly all of these approaches, quench samples must be desalted prior to electrospray mass spectrometry to remove non-volatile salts and other buffer components that would suppress the MS peptide signal. Incorporation of a liquid step conveniently provides a way to desalting the sample and simultaneously provides an opportunity to wash away all deuterium that was incorporated into side chain positions, leaving deuterium label at just backbone image with vastly simplified data interpretation. There is a trapping step utilizing a short column to first capture and desalt peptides, which are then eluted and resolved over a longer analytical column. So there's a short column that desalts the peptides and undeuteriates the side chains. vast majority of HDX-MS protocols use an analytical column packed with reverse phase hydrophobic stationary phases. Most commonly C18. However, shorter hydrophobic chain lengths chemistries have also been used. As the most common mobile phase, such as water, acetonitrile with formic acid, or trifluoroacetic acid, are perfectly suited for this pH range. They need to be kept. Sample cold introduces a large technical hurdle, although it was shown very early in the development that this can be accomplished by keeping the injection loop LC lines and HPLC column in an ice bath. In a refrigerator, okay. Another major analytical challenge, even at 0. All right. Liquid chromatography. Works by separating something. Provides a way of desalting the sample and simultaneously. So how does it work though? How does liquid Alright. Separating a mixture of compounds dissolved in a liquid, a mobile phase, as they are pumped through a stationary phase. Different components in the mixture travel through the column at different rates, causing them to separate or elute at different times. The texture at the end. Okay. I mean, that makes sense. Okay. By separating molecules in a mobile phase using a stationary phase. Molecules dissolved in a mobile phase as they are pumped through a column packed liquid chromatography separating molecules dissolved in a mobile phase as they are pumped through a column in a stationary phase. Different components of the mixture travel through the column at different rates, causing them to separate or elute at different times. The detector at the end of the column measures each separated compound. All right, but for HDX-MS, there's a trapping step. To first capture and desalt peptides that are then eluted to resolve over a longer analytical column. Okay. There's actually a trapping column that desalts and strips these side chains of their deuterium. With nearly all approaches. Immediately provides a way of desalting the sample simultaneously provides an opportunity to wash away all deuterium that was incorporated. Yeah, that's a better way of saying it. A modern the trapping step allows for integration with online protease columns. So the protease is in the analytical column. Okay, let's talk about the LC-MS step. Where is the protease introduced? What is the point of the trapping column? Why does it need to be cooled? How does LC-MS actually work in this context? Online protease columns. So I believe the column itself, yeah, enzyme column. Sad, happy. We're squarely in your wheelhouse now. I might need to change the tone of voice for this. This is getting really annoying, honestly. In a modern, the protease, usually pepsin or pepsin-MS, is immobilized in a small column, a pepsin column, placed in line between the autosampler loop that receives the quench samples and the trapping column, C18. Okay. Immobilized on a small column, placed in line between the autosampler All right. How expensive is this? They got jobs. Let's see. In France. I guess it's mainly technicians. All right. The trap column is basically a tiny solid phase extraction pre-column that sits between pepsin concentrates peptides. You usually inject a relatively large volume of sample in a very aqueous acidic solvent. The trap retains the peptides strongly while most of the salts flow through to waste. So the salts go through? You can load at one flow rate, then switch valves so that the analytical gradient elutes peptides from the trap to the main analytical column. Okay. After you quench, you've slowed it, but you haven't frozen it completely. At any time the peptides set in H2O, you risk back exchange. Once you quench. Okay. Mostly water, formic acid, acetonitrile. Okay, I think I'm getting it. So please concisely tell me the path the proteins take. From the test tube. Explain the point. Explain the purpose of each check point. So I think peptides, or the protein gets quenched with acid. So that's a column itself, I think. Okay, so now it's a quench buffer. Test tube to quench buffer on ice. What happens? You mix the labeling reaction with cold, quench buffer. And this denatures the protein as well. So the quench sample is loaded to the purpose precisely correct. What happens? The denatured protein through the pepsin column and is digested into peptides online. So then the pepsin column goes to the trapping column, bind to the trap, salts and small molecules wash through. A solvent gradient elutes peptides from the trap to the analytical onto the analytical, separating them over a short cold gradient. So the trapping column and the analytical column are both C18. So is the trap in the analytical LC column both C18. Do we after all of the salts and small molecules leave from the trap, we basically switch solvents so they are mobile. Reverse phase. What is reversed phase? Non-polar stationary phase and a polar mobile phase. Why is it called reverse? I guess they have to define something to, or say something to separate the two. It's a separation that uses non-polar stationary phase and a polar mobile phase. So the hydrophobic regions are the ones to leave last. Both the trap and a reverse phase. Differences are more in the format than chemistry. Short, fat, larger particle size, good for quickly grabbing and concentrating the peptides. Good for actually separating peptides with decent resolution. Some systems tweak this. Both sticky for peptides, not for sticky for salts. What happens after salts leave the trap? Mobile phase is very aqueous, like very low organic peptides stick to the do not stick and are washed. Okay. The valve switches so the gradient from the LC pump now flows through the trap into an analytical column. Solvent composition isn't changed over time, more from mostly aqueous to gradually higher, like acetonitrile. The organic content rises. Peptides let go of the trap are carried through, then further separated. You could say after the salts leave the trap, we basically switch solvents so they're mobile. That's essentially right with these small tweaks. We don't literally swap bottles, change the ratio. Gradient from, okay. All right, makes sense. Okay, so works by separating molecules to solve the mobile phase. They're pumped to destination. We're actually. So the way it works in HDX MS is that we first dump the solution into a dump the protein into a acidic buffer solution, which is then passed through this, then denatures the protein and is fed into a pepsin stationary phase column. Right, pepsin's the first step, right? Quench buffer, immobilized protease column. Um, this to chop up the protein. This then is fed through a small column, a small C 18 column to trap the peptide molecules while letting the salts and small molecules freely pass to concentrate the protein. The protein is then, I think the term is eluted. Yeah. The protein is then eluted to an analytical column which is a reverse phase C18 column, which will separate peptides according to their hydrophobicity. The peptides are nebulized. It's a cool word. Okay, basically turned into a mist and ionized by electron spray. To be fed into the MS where it reads out an isotopic envelope and mass to charge ratio. Oh. So that's how the LC part works, basically. So now how does mass spec work? Ionizing a sample, separating the ions, using electromagnetic fields, and then detecting them to produce a mass spectrum. This process allows for identification quantification. Vaporized sample, ionization. So what was the point of this bend here? Okay, I think I get it. How does the MS work now? So in the beginning, there will be mainly, what was it, non-hydrophobic peptides fed into the hey parakeet. Explain the instruments and how explain the instrument, the point of ionization, the magnet, and the detector. Explain how the spectra changes as the peptides are eluted through the column. It's going good. Learning how a mass spectrometer works, basically. Just trying to make sure I know everything before the oral exam. That's fun. Yeah, Desmos is nice. You know your quadratic equation? What math is that? Chemistry's math too. Applied algebra? Perfect. Okay, yeah, I see. It's a class. I think that's probably one of the last classes that seemed pretty practical. Perfect. Exactly at time to zoom in on pathway style. What physically happens in an NS inlet? Once peptides loose from the analytical column, the LC effluent goes straight through the ESI source, which sits at the front of the mass spec. Liquid exits a tiny metal capillary. A high voltage is applied between the capillary and the MS inlet. This pulls the liquid into a fine charged spray of tiny droplets. As the droplets fly, solvent evaporates, droplets shrink, charge density increases with Coulomb explosion. Eventually, you're left with bare peptide ions in the gas phase, mostly multiply protonated, without blowing them apart. Soft ionization, so you can weigh intact peptides and keep their deuterium levels. Okay. Yeah. I think anything's pretty interesting to learn. It just depends on like the teacher really. So I didn't really like English class, to be honest. The magnet mass analyzer sorts ions by mass to charge ratio. After ionization, the ions are pulled away from the mass analyzer. The exact hardware depends on the instrument, but conceptually they are separate ions based on mass to charge ratio. You mentioned a magnet, which is historically accurate for magnet center instruments. Quadrupole. Oh. Yeah. Oh, the Epstein stuff. I try to like actively avoid learning anything about politics. All of it's a charade. I've never even heard of that. Frankfurt School, I've heard a lot about them actually. It's like PSYOP class. Yeah. Previously, back in the day, most of the information was kind of distilled through like radio waves, and they had more control over that kind of thing. And now with the internet, anybody can pretty much spout anything they want to. So I think the strat now, at least in terms of like the government, is just to overload everybody with as much information as possible. Um, there's a conspiracy theory that like the CIA invented conspiracy theories so that we couldn't distinguish which one is true or not. It's very meta. Weimar Republic. Yeah, is this Nazi stuff? Marxist professor. All right, good luck. Thank you. The detector turns ions into a signal. Okay, so quadrupole plus TOF. What's that? Time of flight is a hybrid mass spectrometer. It combines quadrupole mass filter with the time of flight mass analyzer to achieve high resolution, accuracy, and sensitivity. I need to talk to my friend about this. She works in mass spec. This looks insane though. Oh. Ion mirror? What the hell? Can you guys know what this is? Let me know. Alright, so hit a detector or induce an image current. Now imagine watching the MS scan over time while the LC gradient runs. Early in the run, mobile phase is very aqueous, low organic. Only the most hydrophilic, weakly retained peptides elute the spectrum. Fairly simple, just a few peptide charged state clusters, lots of background from solvent, but salts are largely removed at the trap. Middle of the run, organics, more peptides. Spectrum becomes busier, many different MZ peaks. Each peptide appears as one or more peaks corresponding to doubly and triply charged. Each charge state shows as a small isotopic envelope. If you track your peptide across the signal rises, and then falls. Okay. Okay. Nice. Interesting. Um, so if they ask me like what an MS is, I really honestly couldn't tell them. Um, I mean, I would say it's just like a detector. Electron multiplier. Yeah, see, I don't have to know this crap, really. I don't think my professors know about this. So in one sentence, and if you can you answer the question of what an MS instrument is and why it works in this context. Let's see what it says to that. That weighs ions. It turns molecules from solution into gas phase charged particles, separates them, and measures their abundances. It weighs ions. LC separates and then the MS exact masses because deuterium. Okay. Okay, I think that's enough for that. Oh man, we probably spent like, I don't know, 30 minutes on this slide. At the left, we're in with a time-resolved series of centroid masses that tells you how much deuterium incorporation has occurred in solution, typically shown as percent fraction uptake over time. So that's what that means. Should be going from gray to blue. Okay. Simple enough. So why are the results so hard to interpret? A better question would be, what factors influence the exchange process? Why do some regions exchange a lot, which is shown in red, and others exchange very little, which is shown in blue? So there are many ways to explain how exchange occurs. Instead of B fact, oh, there's a note to myself. Some of the common ways people approach doing this are with information like solvent accessibility surface area. So then it'd be RMSF / B factor and number of H bonds. As you might imagine, the correlation of these features to its experimental uptake profile is not great. Otherwise, the problem would have been solved long ago. Today, the most popular method for predicting uptake profiles is called the Best and Vendor-Scolo method. This is a pretty straightforward method that assumes first the opening and closing environment surrounding a that the would be the opening. No, I think it's opening / closing, actually. The environment's running is way faster than the chemistry of exchange. So in effect, the observed rate of deuterium incorporation is gated by the probability of that site opening, which is represented by the formula here. I think I have a better way of explaining this in the paper. Structural closing. Yeah, so let's stick with that. The closing each amides exchange is governed by frequent opening leading to uniformal. Yeah. Okay. Closing is way faster than the chemistry. So the observed rate is gated by how often the site opens. Yeah. Okay. We can quantify the degree of gating by computing something called the protection factor from the first equation. The higher the protection factor, the lower the probability of site opening. So that's what this shows here. It's the intrinsic rate of exchange over the observed, which is equal to 1 over the probability of opening, right? Yeah. So to calculate protection factor, we would look around the nitrogen atom and count how many all atoms mix, and then the number of within a set radius. In practice, you would do this across an ensemble of structures from MD and tune the alpha and beta coefficients to get a general model for other proteins. To get a rate of uptake across time, you would divide the residue's intrinsic rate by the exchange by the protection factor to get a slowed rate of exchange, which is used to calculate the fraction uptake at time t. That makes sense. What could they ask me here? could ask me like what EX1 is, which I think I could explain pretty easily. EX1 is when the chemistry is faster than the rate of closing. So instead of like a unimodal isotopic envelope, it'd be like bimodal, where like one population would just decrease, the other one would increase, rather than like a smooth transition between the two. That's due to the fact that multiple deuterium can stick to that region at one time. Trying to think what else they could ask here. All right, so here's one just case where this model is used to predict the uptake of cytochrome C. As you can see, rank ordering as indicated by Spinel is actually well modeled, but the accuracy of the scalar value is not so good. So is there anything out there that is better? So let me break down what the best model would be. So I want to say the best hypothetical model. I want to say like a good, what makes a good, what makes a good model? So I need to change that for all of them. Okay. So let me break down what makes a. So let me break down what makes a good model. There are basically two things we want to model. We want from a model: accuracy and interpretability. So the first thing we want to see is if this model can generalize to protein structures, to unseen protein structures. Next, we want to make sure that there is no significant prediction bias to peptide length, time point, or residue type. We want to outform the BV model in terms of static structure predictions and MD ensemble reweighting. I'll get to what this means later on, but basically we want to predict across frames and look at those frames that have the best prediction and see if the structures make sense. No, it's not. We want to, I'll get to what this means later on, but basically we want to predict across frames and have some procedure. takes our prediction and fits it to the experimental data without overfitting. This will be our benchmark. Next, we want to see if our model can be used to predict changes to uptake upon ligand binding. And finally, we should look at what the model says and see if the results align with our intuitions about the chemistry of exchange. So moving on to interpretability, we need to think carefully about how we structure the problem so that we are not just getting a number from a black box. So the predictions need to be physically motivated. So the model architecture needs to be physically we want to predict uptake per residue so that we can see local effect. So we can see what local effects determine the rate of exchange, rate of uptake for a given atom. This would also address the limitations of HDX-MS experiment itself, since we do not have per residue resolution. Ideally, we should end up with a new equation for uptake that is easy to digest and use later, so that for knowledge transfer. So now let's talk about the approach we took to get us close to this grocery store list of model demands. So here is the basic pipeline for getting to the model we want. Would they ask any questions here? Okay, why does it need to generalize to unseen protein structures? Because that's the only way we can know if the model is learning something. I don't know. Why are those three ways to measure bias? Well, we basically want to see if the model is like cheating in some way. And what are the limitations of prediction accuracy, basically. But if it doesn't have like I mean, what are some other ways to measure bias here? I really can't think of many more. We could do like pH or percent deuterium concentration, look at those other things. Better than the BV. So why is the BV model your benchmark? Well, I mean, for one, it's like the easiest to implement. Really, that's the main reason. It's fast, and it's used commonly in the context of MD. So yeah, I really don't think there'd be many questions here. All right, so here's the pipeline. So first we would start with a static protein structure. The quickest way to get this is through AlphaFold. So we'll use that to generate our structures. We'll use that first to generate our structures. The model itself is a small multi-layer perceptron with only one hidden layer. Our model comes out to around 200,000 parameters. For a reference, AlphaFold has around 93 million. So our model is considered very small, lending itself to run quickly and be interpreted easily later. So the outputs of the model predict weights and rates for this multi-exponential function. We will set the number of exponential functions to use for each residue as a hyperparameter. We found 4 exponential functions perform just fine for this problem. To be honest, this is probably overkill, and we could definitely tune this later. Recalling earlier that HDX-MS outputs a time course for uptake for a peptide. So to bridge from residue level predictions, we simply sum individual residue predictions along the length of the peptide to get out the peptide level uptake. This means we are predicting latent parameters, so we have to keep an eye out for the model generating degenerate solutions since there's no direct loss we can compare per residue. So after training, we are left with a black box model that predicts weights and rates. To address interpretability, we will use these neural network predictions as targets for a surrogate model to reproduce using ridge regression. We'll just say like linear. Ridge regression is yes. Okay, so here they're probably going to ask me like, how does like a machine learning model work, right? So we need to learn some calculus here. Fireship. Shut up, Fireship. So, in short, basically, okay, so this is would be supervised learning. There's a regression task. So first off, our task is one of regression, and we will use supervised learning. Supervised learning takes inputs and maps and constructs a multi-dimensional can I spell? Multi-dimensional non-linear function to map the input to the desired output. The weights are updated using gradient descent. So I need to understand the math behind gradient descent. So I learned this once before. All right. So the question here is, how does a machine learning model update its weights? All right. A neuron labeled J is receiving input from predecessor neurons consisting of the following components: an activation, discrete time parameter, an optimal threshold, an activation function, and it produces an output. It's simply the identity function. Yeah, so backpropagation is where it gets a bit confusing. Weighted sum. The first step in a neural computation involves aggregating the inputs to a neuron, each multiplied by their respective weights, then adding a bias term. This operation is known as the weighted sum or linear combination. Mathematically, it is expressed as that. Where Z is the weighted sum, WI represents the weights, the ith input, xi is the ith input to the neuron. Bias term is a unique parameter that allows adjusting the output along with the weighted sum. It's basically like a y-intercept kind of. Because it constitutes the raw input signal before any nonlinear transformation. It allows the network to perform a linear transformation. Yeah. Oh, wait. Yeah. Yeah, so this is the core right here. Consists of two forward pass. Is the chain rule of calculus, which is used to calculate the gradients of the loss function for each weight by multiplying the gradients of the layers behind it. So these are partial derivatives. This is not up here. None of these are up here. Process B, the biases. I think I'm going to ask ChatGPT to do this. Run through how a small neural network updates its weights in response to an input using gradient descent with dummy numbers. So what is the chain rule? A function within another function. For example, the derivative sine x is cosine. Okay. So what would be the composite function for the final layer? Smallest non-trivial network. X1, X2. One neuron with sigmoid activation. Okay. Input, target 1. We want the network to output 1. Initial weight and bias. Boom. Activation sigmoid. The loss mean squared error. Okay. So the forward pass is a linear combination. So, wait. How many neurons do we have here? I guess 2. Plug in the numbers, get -30. Or 0.3. Current loss is that, we want the gradients, the loss with each parameter. We'll use the chain rule. So this is what we're optimizing, is the weight 1, weight 2, and the bias. Okay, so this is the derivative of that. The gradient with respect to y. For the sigmoid. Pre-activations. Wait, what? All right. So there's two inputs. Yes, there are two inputs. There's only one neuron. That one neuron takes both inputs and does that. Two inputs, one neuron. Why is there... What's the point of having two inputs? Why does each input have a weight? Okay. Let's see. Yeah. Right. Okay. I recall. All right. So these are just the features here. So you plug in the numbers, right? and it's just a linear combination of those, so minus 3. And so we want to scrunch that between 0 and 1, so that's what the sigmoid does. And then we can do the loss. So this is the mean squared error. So backprop, we want to compute the gradients of the loss with each parameter. So it'll be the weights and the biases. We'll use the chain rule. So if this is the loss, the derivative of that, so just take that out, and then so it'd be 2 times this, which equals that, right? So then we plug that in. So why do we take? Okay. And so where does this come from? For sigmoid, pre-activation Z. I am not following. Why are we doing this, and where did you get this equation from? What do you mean by pre-activation? See, ChatGPT assumes I know too much. But this kind of is like the last main thing, I would say. Maybe I can explain this actually. It's pretty easy to understand. Max entropy reweighting. Because I think I know how to explain it. What is pre-activation? A single neuron does two steps: linear combination, non-linearity. Yet, no non-linear linearity. God, this Z is just a number. People call this the pre-activation or net input because it's what you get before applying the activation function. So we take that Z, squash it through some activation function, the sigmoid, and the Y is the activation, the neuron's input. Let's see. So pre-activation Z, so the sigmoid acting on Z is Y. Okay. So here it's saying the derivative of the sigmoid equals that how do I do this? um, I need to take a calculus class again. I think Mathematica can actually do this. So we can do x 1 over 1 minus e to the negative x. Yeah, no, it's 1 plus e to the negative. Step-by-step solution. Ugh. So there's rules. Okay. The derivative fund, you can use the quotient rule and the chain rule. So the quotient rules, when you, it's like when two things, yeah, I completely forgot about that. There we go. Chain rule and the quotient rule. We'll go through the calculation steps and decide which rules are applied. It's a fraction, but the numerator and denominator are differentiable. We can use the quotient rule to find the derivative of the whole function. Um, dn short for denominator, and num short for numerator. So the denominator times the derivative of the numerator, which should be just derivative of 1 is 0. And then the derivative of the denominator would be that, I guess. But like the derivative of e2 e to the x, or e to the negative x. So this is the chain rule then. It's a function within a function. One plus e to the negative x. Okay. God, it's been so long since I've done any of this shit, honestly. It's kind of sad. I blame COVID. So this is the chain rule. So e to the g is e to the g. And so the derivative of negative x would be -1. And then so okay, I get that. Yeah, so anything like the exponent is just like 1 over. Okay, but I just keep it like this then. All right, get that. So we're using the quotient rule, then within here it'll be the chain rule. So chain rule right there, then the quotient rule. Oh yeah, explains that. Okay, get all this. Split the function into 2 fractions. I mean, this is just algebra at this point, right? Yeah, that makes so basically cutting this here. Now it's possible to rewrite this. That makes sense. I get that part. What about this? I do not get this though. Hmm. How did I do this? What? Yeah, okay. I just need to figure out this part. Oh, wait. Oh, I see, I see, I see. Okay. Yeah. Right, so you're basically taking out this of both of these. Okay. Stupid. All right, that makes sense. And that's where you get that from. Okay. Okay. That makes sense too, because y equals the activated z. Okay. Oh, okay. Okay, so there's a chain of dependencies. So weight determines the z, which determines the y, which determines the L. So to get to the weight, we have to figure out the L, the y, the z, and okay. Okay. This is making sense actually now. So L, so we gotta go to the Y, and then the Y to the Z. So the partial derivative of Z, depending on the weight, is X. Um, so the derivative of Z with respect to W, hold on. Okay. So the derivative of this is 1, which is why it's x1. Okay. So numerically, to the gradient descent update rule. Update to the weight is that. It's the old minus that times the theta. What's theta in this case? The theta would be that. Oh, theta is just whatever that is. So is this the nudge that we're doing? Or is this the result? Oh no, it's the new. These are the new weights. All right, it's coming to me, I think. Okay, I do probably need to on my own time, like write this out on a piece of paper, but I think I understand. But yeah, that'll be something I do later on my own time. It makes sense though. So basically what you have to do is, so with the neural network, there are inputs, there's a neuron, you have to have an activation, there's an output, and then there's a loss. So going back from the loss, you have to compute the gradient from that. So it's the loss with respect to y. Yeah, it's the derivative of L with respect to y, which is just y minus y. And then from there, you need to figure out the gradient with respect to z, which is that. So that's the derivative of the sigmoid function, which is equivalent to this. So L to y, y to z. So to get these multiply together with the chain rule. Well, this, can you show me the full nested function to get to the I want to see that. All right, so let's look at this for a second. It's kind of not what I was thinking of. All right. I'll look at that later. I think right here is a good stopping point, actually. I have a meeting pretty soon, so. All right, I'll catch you guys later.